Section 11.2, we're going to look at areas of trapezoids today, and then areas of rhombuses and kites as well. And so we're going to start out discovering coming up with this formula for the area of a trapezoid. Remember, by definition, a trapezoid has one pair of opposite parallel bases. So base 1 and base 2 here are parallel. You notice I have the height labeled. Now there are two ways actually to come up with this formula. The first way is I'm going to copy and paste this trapezoid. Now the reason why is because, picture this, if I copy and paste, can you picture how I can turn a trapezoid into a parallelogram? The problem with trapezoids is that their two legs are generally at different angles, but if I copy and paste, hopefully you're seeing that I can take this and rotate it around and match up the corresponding legs. And now the ultimate shape is a parallelogram. Well, in that case, a parallelogram, the area is base times height, right? For a parallelogram. But the base is actually this entire thing for the parallelogram. Oh, well that was the sub 2, by the way, it just says base 2. This is base number 1. But if you look at like the entire base, it's the base 2, the bottom base, the original, and base 1 because it was flipped over. So what would you do with those two to get the total? You'd add them together, right? Base 1 plus base 2 to get the whole thing. Well, so the area of that parallelogram then, the base is actually adding the two original bases of the trapezoid quantity, so I'm putting parentheses. The height of the parallelogram I formed is still just the height of the trapezoid. But here's the thing. We have two trapezoids making the parallelogram. So I don't want the entire thing, base 1 plus base 2 times height. That's two trapezoids. I only want half of that, since there were two of them. Now this is the formula for area of a trapezoid. The area is 1/2 of the sum of the bases. So you add the two bases in the trapezoid, they're going to be different, obviously. And then you multiply by the height. So the most complex area formula we've had so far. I said that this was one way to find this formula. There's another way as well. So I'll get rid of this stuff. And I also need to get rid of this second one here. I can actually draw in a diagonal here. One diagonal, because now what have I formed? These are two triangles, aren't they? So to find the area of the triangles, I'm going to add them together. Now a triangle is 1/2 base times height, isn't it? So what about the top triangle here? The area of that triangle is 1/2. Now the base of that triangle is the base sub 1. And the height would go from a vertex, actually from a vertex at a right angle to the opposite side. So it is the red height. Plus I need to do the other triangle. In red, I guess. Area of that triangle is again 1/2 base times height. The base of this triangle is base sub 2. The second base of the trapezoid, and the height is still h. And look, I can factor out. You say I got things added where I have half in both. I'm going to factor out half. I have height in both. I'm going to factor out the height, and then I'm left with base sub 1 plus base sub 2 is the only things left after I factor out 1/2 and height. And notice this is the exact same formula. It's just that the height was moved to the end. But they're all being multiplied 1/2 times the sum of the bases, add the bases together, times the height. Let's practice this. Find the area. I'm assuming these are trapezoids. Actually, I don't even need to assume on this. Because of the right angles here and here, the consecutive interior angles are supplementary. These add to 180. These lines have to be parallel. And now the area is 1/2 of what you get when you add the bases together times the height of that trapezoid. Now if you're thinking back to the one where I copy and pasted, it's half because there's two parallelograms. When you copy and paste this and you add 9 and 6, you add the bases together. I know these are the bases because they are parallel. The height, oh wait, the height has to go at a right angle between the bases. Oh yeah, well this is actually the height. This leg ends up being the height because it is at a right angle to those sides. So times that 4. And I can go one step further here. 9 plus 6 being 15 times that 4. And the area is 30. No units given, but units squared. Okay? Oh, and your dresser is a trapezoid. There's actually a lot of bookshelves I've seen in dressers that are trapezoid in shape. I'm assuming these are isosceles trapezoids, right? These legs would probably be congruent. I know that the top of the dresser is 12 inches, the bottom is 18 inches. And this would be the height, right? Measured from the floor. It's 20 inches tall. So with the area of a trapezoid, you do 1/2 the bases added together times the height. And the bases are 12 and 18. Add those together, get the total base if you flipped it over, times the height, which is at a right angle to the sides, which is 20 here. 12 plus 18 would be 30. Times that 20. And so 300. The units are inches, so inches squared for that area. And there we go. So practicing area of a trapezoid today, and now we're going to come up with the area of a rhombus and area of a kite. Now the thing that you need to be able to find either of these, they're actually going to have the same formula, is I need to draw the diagonals. There was a property of the diagonals of a rhombus and a kite that hopefully you remember from our last few chapters ago. What angle do those diagonals meet at? I hope you can tell that they do meet at a right angle. They're perpendicular. This was only the case for a kite and a rhombus. Well, and also a square, because the square is a rhombus. But those diagonals are perpendicular. And what I'm going to do, since we're going to talk about the diagonals, and we're going to use them in the formula, is I'm going to call one diagonal diagonal sub 1, diagonal 1. It'll be the whole entire thing. And then this will be our diagonal 2, this entire diagonal. And then same thing here, we'll have diagonal 1 being this whole thing, diagonal 2 being this entire diagonal. You actually do have these diagonals bisecting each other in a rhombus. So if you remember that you have these congruent and these congruent. In a kite, only this diagonal is bisected. Okay? But what we're actually going to do, the way we're going to come up with this formula, is I'm going to take each of these right triangles that are formed, and I'm going to like copy and paste them and create out here, oops, a copy of those. Oops, I got to adjust this a little bit. If you notice here, I copy and pasted this triangle, which is part of the rhombus, to here. Copy and pasted this triangle, which is part of the rhombus, to here. Copy and pasted this triangle, which is part of the rhombus, to here. And this triangle, part of the rhombus, to here. I just doubled the size of this rhombus. Now, if you think about the area of this rectangle, the area of a rectangle is just base times height. Well, what's the base? Well, this length is the same as the length of diagonal 2. This height is the same as diagonal 1. The area of the rectangle is just diagonal 1 times diagonal 2. But remember how I copy and pasted each triangle, so I doubled the area of the original rhombus? So really, I don't want just diagonal 1 times diagonal 2. I only want how much of that? Since I copy and pasted each of those, I only want 1/2 of diagonal 1 times diagonal 2. Because this would give me the entire rectangle. But again, that's, doubling every triangle there. Area of a kite is the exact same. It's going to be 1/2 of diagonal 1 times diagonal 2, because once again, I copy and paste these little triangles right here and here. I copy and paste these larger right triangles up above here and down below to the right here. And now you have again this rectangle. The area is diagonal 1 times diagonal 2, but the rhombus, the kite itself is only half of that. So the formula for rhombus and kite are the same. It's 1/2 of the two diagonals being multiplied together. And why? Because the diagonals meet at a right angle. You have these right triangles that you can sort of copy and paste onto themselves to make a rectangle, but you're only going to want half of that rectangle's area. So let's try these as some examples here. Find the area. This is a kite. because you have two congruent sides here next to each other and two congruent sides here next to each other. And I know the area of a kite is 1/2 of the two diagonals multiplied together. In this case, I do know both diagonal lengths. Diagonal 1 is 14. I can tell that that's shown here. The second diagonal, 6 inches here. And we've got 42. For my area, it is inches, and area would be inches squared. Okay. What shape is this? All congruent sides, so it's a rhombus. Again, I'm doing 1/2 of the two diagonals multiplied together. Area is 1/2 of the two diagonals. The two diagonals will make that rectangle, but I only want half of it. Oh, okay, this is 30 though. Only this length here. But guess what? You know that the diagonals of a rhombus bisect each other. So if this much is 30, the entire diagonal is 60. For the second diagonal, if this much is 40, again, this is bisected. This diagonal is bisected, so 40 and 40. That whole diagonal is 80. And we're getting 2400. Yeah. For an area, label would be units squared. Here we're talking meters squared. So area of rhombus and kite. Let's try another example where I'm solving for a variable here. I know the area of a kite's 80 feet squared. Area of a kite is 80 feet squared. One diagonal is 4 times as long as the other. One diagonal is 4 times as long as the other. Let's find the lengths of those diagonals. Well, all I have is the area, and then I need to find both diagonals, so I'm going to have to call them something with the same variable. If one's 4 times as long as the other, if I called this diagonal x, and this one's 4 times as long, it would be 4 times the length of that one, or 4x. So, if we're talking about a kite, I need the formula for area of a kite, which is 1/2 times the two diagonal lengths. 1/2 diagonal 1 times diagonal 2. In this case, I know the area is 80, so I'm putting that for area. It's 1/2 of the two diagonals multiplied together. One diagonal was just x, and one diagonal was 4 times that, so 4x. And now it's 1/2 times x times 4 times x. Multiplied numbers, half of 4 is 2. X times x would be x squared. Divide by 2 to get x squared alone, and 80 divided by 2 is 40. And now I'm taking the square root of 40. Not a perfect square. We'll round to 2 decimal places. X is 6.32. And let's see, this would be in feet, right? Because area was feet squared. And the lengths of the diagonals then. Well, diagonal 1 is just x, 6.32. Diagonal 2 is 4 times that. I'm going to do times 4 the number I had sitting in my calculator. So not just 6.32, but it went on forever. 25 I'm seeing like 298, so actually 25.3 would be approximating diagonal 2 as close as I can. Let me check if I get 80. I know these are both rounded, so it won't be perfect, but if I do 1/2 times 6.32 times 25.3 and multiply the diagonals times 1/2, I get, 79.948, so real close to my 80. Okay. And last thing today, but probably most important as we continue on in this chapter, is thinking about area and how many square units are in like conversions in a sense. So how many square inches are in a square foot? And some of you are going, well, isn't it just 12? Because there's 12 inches in 1 foot, right? But this is not just an inch. This is not just a foot. This is not measuring on a line. This is talking area. This is talking square units, actual physical squares. Now, if you picture this, yes, there are 12 inches in a foot. So if that's a foot, I mean, I know it's not, but let's say this is 1 foot. Wouldn't that be then split up into my 12 inches? 1, 2, 3, 4. Okay, there's my 12 inches, making up 1 foot. But this is a square foot, which means it's also 1 foot in this direction. Which means it's also 12 inches in this direction. So it's 1 foot by 1 foot, but it's 12 inches by 12 inches. Okay, so 1 foot by 1 foot, 1 square foot, is actually 12 times 12, or 144 square inches in 1 square foot. So keep in mind, because of that two-dimensional, I mean, I could draw this grid. I could do all the lines here, 12 lines, 12 lines. It would be 12 by 12, 144 square inches in a square foot. Or you could think of it this way. 1 foot is 12 inches, right? Those are equal things. That's like a fraction that equals 1. But I'm doing a square foot, so I'm doing a foot by a foot, which, again, a foot is 12 inches. And that's what we did right here. So this is 1 square foot is actually 12 times 12, or 144 square inches. Okay, so keep in mind these conversions. It's not as straightforward as you think when we're talking area. You're going to have to basically square the number just like it's unit squared. You're going to have to square the conversion. So if I then asked you how many feet squared are in a yard squared, well, okay, how many feet are in a yard in general? There are 3 feet in 1 yard, right? But this isn't a yard. This is a yard squared, so it's 1 yard by 1 yard. It's 3 feet by 3 feet. That means there's 9 square feet. 3 times 3, 9 square feet in 1 square yard. Okay? And finally, what if I ask you how many square centimeters are in a square meter? Well, wait, how many centimeters are in 1 meter to begin with, just in a line? There are 100 centimeters in 1 meter, but this is not just a meter. This is 1 meter by 1 meter. This is 1 square meter. Which means in that second meter, like the vertical one, there's another 100 centimeters. 100 times 100, or 10,000 centimeters squared in 1 square meter. That would be hard to draw, right? 100 by 100, and you'd have 10,000 square centimeters in that 1 square meter. So keep this in mind when you're looking at conversions between square units, talking about areas of trapezoids, rhombuses, and kites today.